Hello, I'm Shaheen,
I'm David.
and we're going to teach you about the foundations of Fourier transformations.
Look forward to it. So if we have here a sample of audio file, looks something like this, complex. The way that sampling works is that we take equal time steps and then we measure this value at each point. So this would be 2, 4, 2.5, 3.5, 0.25, negative 2, 1, 1.5, 6, and 5. With these values, we can then compose a vector. Where every value corresponds to this, and every time step corresponds to a time step here. Then, now let's say that we have a few component frequencies to start off with. With these, we can make the same sort of graphical representations. We could take these and add them up to give us our compound frequency. Any complicated audio wave that we would see in real life is made up of a combination of simple component frequencies. To relate this to linear combination theories, we can say that these are represented by the A, B, and C vectors. And so this complex wave equals C1A plus C2B plus C3C.
So, when trying to solve Fourier transformation, it's good to remember a couple of different tricks. For one, you should always remember that I is equal to square root of negative 1. And from there, e to the I pi is equal to negative 1. And with knowing e is an exponential function, that same exponential function could be equal to cosine and sine. So from here, you should know that e to the I omega t would be equal to cosine omega t plus I sine omega t. And on the flip side, you should know that negative I omega t, e to the I omega t, is equal to cosine omega t minus I sine omega t. That's all. So when solving Fourier transformation, for example, x double dot, which is the second derivative of x in respect to time, is equal to negative k over m times x. When it's trying to solve Fourier transformation, it's good to find a solution in the terms of e to the lambda t, where the real part of lambda will describe the decay rate, and the imaginary part of lambda will describe the frequency of oscillation, as the growth decay rate is how much the oscillation will start to shrink or grow, and the oscillation rate, the frequency, will be as it gets more, the period will get smaller or larger. So when trying to solve this, you say lambda in this example is equal to plus or minus square root of negative k over m, which will be simplified to eventually to plus or minus I omega, where omega is equal to square root of k over m. And within that same statement, omega is also the natural frequency, which is the part you want to get out when you're trying to filter. So after putting it in this form, you would thus get, in this equation, you would get e to the I omega t as one solution and e to the negative I omega t as the other solution. And from here, you can write it as a linear combination of using coefficients where C1 e to the I omega t plus C2 I to the negative omega t is equal to x of t. And from here, you could write that in terms of cosine and sine, where it will be C1 times, in parentheses, cosine omega t plus I sine of omega t. Because from before, we said that e to the I omega t will be equal to cosine omega t plus I sine omega t. And then from here, you could also write, for the next part, C2, parentheses, cosine omega t minus I sine omega t will be equal to the same thing as C2 e to the negative I omega t. So from there, you could simplify that to C1 plus C2 times cosine omega t plus I times C1 minus C2 sine omega t, which, if you set A equal to C1 plus C2 and B equal to C1 minus C2, you can simplify that down to A cosine omega t plus I B sine omega t. Where here A is the real part of the frequency, and B will be the imaginary part, which would then get you the decay and the growth rate from A, and then a natural frequency from omega, and then the frequency of oscillation from B.
Thanks for watching!
Thank you again. Have a good day.